Hello, my name is Shivam Kundan. I'll be presenting my report on Raman spectroscopy, which was named after the Indian physicist C.V. Raman in the year 1928 and later won him the Nobel Prize for Physics in 1930. Raman first became interested in the topic of spectroscopy when he visited Europe and saw the Mediterranean Sea for the first time. He was taken aback by how blue it was and suspected there was more to the color than the reflected Rayleigh scattered light from the sky, which was the prevailing explanation at the time. Raman spectroscopy is a practical application of Raman scattering, which is the phenomenon of inelastic scattering of monochromatic photons when they collide with molecules. Traditional Raman spectroscopy involves measuring the vibrational state of these molecules. However, as technology has progressed, especially with lasers and charge-coupled devices, scientists and engineers have invented newer ways of utilizing the data obtained from Raman scattering. All of these techniques fall under the umbrella of Raman spectroscopy. In fact, the modern scope of Raman spectroscopy is so large that there exist scientific journals solely for the purpose of publishing research into this topic. On the right is the cover of the May 2020 issue of the Journal of Raman Spectroscopy, shown along with a commercially available Raman microscope. The picture on the bottom shows one of Raman's original analyses of the spectrum of benzene, with the resultant line showing benzene's molecular fingerprint. Raman spectroscopy techniques are used for a broad range of applications, such as providing distribution maps of chemical compounds and material properties. This image shows a hyperspectral Raman image of a 19th century sample of cement, showing the presence of a particular crystalline defect. More relevant to us is the use of Raman spectroscopy in the characterization of materials. As shown in the diagram here, spectroscopy can help us quantify many of the properties of a given sample, such as for future semiconductor materials research. As a final example, consider this comparison of the black pigments used in two different parts of this Greek vase to determine whether it is authentic or not. The key difference here is the presence of iron, since Greek artists used clay rich in iron oxides for black paints, and forgers do not. When considering Raman scattering, we can think about the physics in one of two ways: the classical wave interpretation or the quantum particle interpretation. In the classical interpretation, light is considered as EM radiation, which contains an oscillating electric field that interacts with a molecule through its polarizability. The polarizability is determined by the electron cloud's ability to interact with an electric field. For example, soft molecules such as benzene tend to be strong Raman scatterers, while harder molecules like water tend to be fairly weak Raman scatterers. In the quantum particle interpretation, light is thought of as a photon which strikes the molecule and then inelastically scatters. In this interpretation, the number of scattered photons is proportional to the size of the bond. For example, molecules with large pi bonds, such as benzene, tend to scatter lots of photons, while water with small single bonds tends to be scattered quite weakly. The Raman scattering effect can be quantified using the classical interpretation by considering a simple diatomic molecule as a mass on a spring. And as with all springs, we will begin with Hooke's law. In equation 1, the atomic mass is represented by the m1, m2 divided by m1 plus m2 term in the beginning. The displacement is represented by x1 plus x2, and the spring constant, which in this case is a measure of the bond strength, is represented by k. By replacing the reduced mass term with mu and the total displacement x1 plus x2 with q, the Hooke's law equation can be simplified into equation number 2. Further solving for q, we obtain equation 3, where Vm is the molecular vibration. Each molecule will have its own unique vibrational signatures, which are determined not only by the atoms in the molecule, but also by the characteristics of the individual bonds. When incident light interacts with the molecule, it induces a dipole moment P, equal to the product of the polarizability of the molecule and the electric field of the incident light source. We substitute polarizability for displacement using the equation at the bottom. We arrive at an equation which shows two resultant effects from the interaction of a molecule with incident light. The first effect is called the Rayleigh scattering, which is the dominant effect and results in no change in the frequency of the incident light. The second effect is the Raman effect, which can be shown to shift the frequency of the incident light by plus or minus the frequency of the molecular vibration. Expanding this equation further, we can get equation 6, which shows that the shift in frequency is either by plus or minus the frequency of the molecular vibration. We can visualize this phenomenon using a Jablonski diagram. When an incident photon excites a molecule into a virtual energy state, one of three outcomes are possible. First, the molecule can relax back down to the ground state and emit a photon of equal energy to that of the incident photon. This is an elastic process and is referred to as Rayleigh scattering. Second, the molecule can relax to a real phonon state and emit a photon with less energy than the incident photon. This is called Stokes shifted Raman scattering. And third, the third potential outcome is the molecule is already in an excited phonon state, is excited to a higher virtual state, and then relaxes back down to the ground state, emitting a photon with more energy than the incident photon. This is called the anti-Stokes Raman scattering. In summary, Raman spectroscopy is a practical application of the Raman scattering effect. Raman spectrometers employ this effect by using three primary components: the excitation source, which is usually a laser, the sampling apparatus, and the detector, which is usually a charge coupled device. Thank you.